All right, so we begin immediately. Question 4 begins with 4a, and it says determine whether v1, determine whether v1 equal to those people that will come to use these videos maybe in the comment sections will be the ones that will enjoy the most, because by then would have given some editing to it to reduce the length, because here we include the writing of the questions and all that. So but then we would have to cut out some of the things and then reduce the length, so it will be of course length shouldn't be a problem for us anyway. Okay, so we have v1, v2 and v3. Our v3 is equal to 2, 1 and 3. Okay, so determine whether it's these three vectors, whether they span the vector space R3. Okay, so whether they span R3, that's what the question is saying. And how do you determine whether a set of vectors span a particular vector space? Of course, like we said, it has to be the vectors needs to be linearly independent, and they need to to span, they should form the linear combination of any any vector in R3 should be a linear combination of v1, v2, v3. That's what we want to achieve. So solution. Okay, so we start by saying we want to let what should I say? Let K1, K2 and K3 be in R3. Okay, so we are choosing an arbitrary vector in R3. So we want to show that let me call that K1, K3 we can still go this way. So we want to show that K1 v1 plus K2 v2 plus let me not use this same K to do this thing. All right, I've picked K1, K2, K3 in R3. So I want us to show that there are scalars. Maybe let's use x1, x2 as our scalar. So we have x1 v1 plus x2 v2 plus x3 v3. Okay, so this should be equal to our k. So and our k is the k1, k2 and k3. That's inside R3. Okay, so we want to show that this is consistent, so that so let me call this k. All right, so we want to show that this equation is consistent. That means has a solution for all k in R3. Okay, so that's what we want to achieve. All right, and to do that, all we need to do is to form a matrix by using the vectors v1, v2, and then confirm that their determinant is not 0. If their determinant is 0, then they do not span R3. But if their determinant is not 0, then it spans R3. Okay, so let's form that that matrix. Okay, so let our matrix A be equal to of course this will form the columns. So 1, 1, 2, then 1, 0, 1, then 2, 1, 3. Okay, all right, so you can see actually that these vectors are the same whether column wise or row wise. Okay, so and by the time you determine the the determinant of this particular A, so okay, I can leave it like this actually, and then I can write here. So this implies that the determinant of A, which is equal to 1, of course you pick this, then multiplied by the adjunct of this, which is 0 minus 1, and then minus 1 here, into determine this other one, which is 3 minus 2, and finally plus 2, which is into 1 minus 0, okay, and that is going to be equal to, this is minus 1 times 1, which is minus 1, and this one is 1 times minus 1, and that is minus 1, and then plus this one is 1 times 2, which is 2, and you can see that this determinant is equal to 0. So if the determinant is 0, it implies that v1, v2, v3, what am I writing? Okay, v1, v2, yeah, I was correct, v3, they do not span. They do not span R3. Yeah, because you see, this is a beautiful way to determine whether a given set is a spanning set, whether it spans a given vector space. All right, so, and this is just what you expected to do for this question A. And then straight away we go to the next one, and the next one says that we should let u be equal to 1 minus 2, 3, and then v equal to 5 minus 13 minus 3. That's v. Okay, sorry, we used uv and then b, and b is equal to minus 3, 8, and 1. So they said clearly the span of u and v is a plane through the origin in R3. So normal to the plane is u cross v, okay, which is equal to that. So it says write the equation of this plane. All right, so they are saying that clearly that the span of this u and v is a plane that went through the origin of R3, and so they are asking us to write the equation of the plane. And to write the equation of the plane, we need to get the normal of u and v, and which is what they already started for us. Okay, so to get the normal remember, let me write it, I, equation of the plane. You have the material, so it will help you. So we need to get the equation of the plane. So we need the normal to the plane. So this implies that normal to the plane is equal to u cross v, and u cross v is equal to, you know our approach, the determinant of ijk and then u and v. So what is our u? Our u is 1 minus 2, 3. What is our v? Sorry, yeah, I'm correct. Our v is 5 minus 13 minus 3. Okay, so what's this determinant going to be? Let me see if I can do that way. So I into this times this is 6 minus this times this is minus 39, so that will be plus 39, and then minus j, let me shift this. Okay, so that's going to be j into this times this is minus 3 minus 15, and then plus j plus k, and our k is going to be this times this, which is minus 13 minus 10, which is plus 10, and that is going to give us the vector. This plus this is 45. I want to write the condensed immediately. This plus minus this is minus 18 times minus, that will be plus 18, and then here will be minus 3. So you have minus 3 here. So that is our normal. All right, and you know that to get the plane equation of the plane from the normal, you will now make use of one of the vectors. Okay, so since the plane passes through the origin, okay, now the plane actually passes through the origin, and the origin is 0, 0, 0. Okay, so that means our equation is going to be, so the equation will be given as your normal, which is 45, into x minus 0, and then plus 18 into y minus 0 as well, and then the last one there I think is minus 3. Okay, so we now have minus 3 into z minus 0 because the plane passed through the origin according to the question. And then from there we will get, remember that this is equal to 0, so we will get that our equation is 45x plus 18y minus 3z, and that is equal to 0. And this is the equation of the plane required. And then the second part says that we should confirm if B is in the plane. Is B in the plane that we just produced? Okay, so how do you determine that? All right, so clearly our B is minus 3, 8, 1, right? That is our B. So let's state that. So you can see does not satisfy, you can see that it does not satisfy the plane equation. Okay, and you can check that. So what is the plane equation? The plane equation is 45x plus 18y then minus 3z equal to 0. So where our B is giving us the vector, where is it? Minus 3, 8, and then 1. That's if you go down a little bit, or up, sorry. If you go up, you will see our B here. Okay, so let's come back. All right, so what are we going to have? You will see that for you to know whether this plane, this particular B is in the plane, just substitute your x as minus 3, y as 8, and then z as 1. And so you discover that you are going to get that 45 into minus 3. Okay, so let's put since. So that if it is equal to 0, then we'll say since this is equal to 0, then B is in the plane. But if it is not equal to 0, then we conclude. So plus 18 into 8 minus 3 into 1. What is that? This is going to give us minus 135. Okay, and then this one will be let me use a calculator to do this at once because of our time. So 18 times 8 is 144. So, and then minus 3, okay, then minus 135. So you see that the sum of all of that is not equal to 0. So since this is equal to 6, which is not 0, so it means that the left hand side is not equal to right hand side. Therefore, we can conclude that B equal to minus 3, 8, and 1 is not part of the plane. Okay, so it's not in the plane. So it's not in the plane. Okay, all right, so and then we can move on to the next one, which is III. So that one says that we should check if B equal to minus 3, 9, and 9 again, if is in the plane, if is on the plane, on that plane also. If is on that plane also. Okay, so how do we do that? So clearly you can see that B is in the span of UV. Of course, if you watch our U and V, let's go up. So see our U and V. You can see that what is our the next b they gave us minus 3, 9, and 9. If you reduce this by 3, you will get minus 1, 3, and 3. Okay, and then is it possible to produce a linear combination of u and v using this? Okay, so and you can check if that is true, right? So you can check if that is possible. But first of all, let's try the other approach that I used in the other one, where we did 45 times minus 3 plus 18 times 9 minus 3 times 9. Let's see what that is going to give us. Okay. Okay, that is okay. Okay, plus minus 27. Sorry, 27. Okay, and that's exactly equal to 0. Okay, so that's exactly equal to 0. So you can see that this is enough to conclude that so this implies that that b, which is equal to minus 3, 9, and 9, okay, is clearly on the plane. Okay, is on the plane. So that's enough to conclude that is on the plane. All right, so it's on the plane. Okay, so you don't need to bother following through many processes to get through to that. Okay, so and then from there we can now progress to the next question. Okay, and so what is the next question, which is C? So C says that we should okay, which is CI, present two vectors that span the solution space of the homogeneous system. Okay, all right, okay. Okay, and this is the system we are given: 10x1 minus 3x2 and then minus 2x3 equal to 0. Okay, so they are asking us to present two vectors that span the solution space of this homogeneous system. Okay, so what can you do? You can see that from here we can begin to do one or two things. And what can we do? We can try to first of all get the of course it's one system, it's a system of it's just an equation. So that means since it's an equation with many variables, so you are going to have free variables, which are x2 and x3. So we can just immediately give names to them. So let our x2 be x2, or you can call them t if you want, and let our x3 be x3. And if that happens, so it means that our x1 is going to be equal to if I divide through by 10 here, so I'm going to, or let's just take this to the other side. So we're going to have 3x2 plus 2x3. So if we divide through by 10, we get that x1 is 0.3x2 plus 0.2x3. Okay, so that means our solution set is going to be x1, x2, x3, and that will be equal to, what is our x1? Our x1 is 0.3x2 plus 0.2x3, and then let me complete that. And then what is our x2? Our x2 is x2, our x3 is x3. And from here we can decompose this into two vectors, vector solutions. So the one of x2 and then the one of x3. You can even put the one of x1 and then if you want. So this is going to be 0, 3, x2 here is 1, x2 here is 0, and that's multiplying x2 plus, then for x3 you are going to have 0.2 here, no x3 here, and then x3 here is 1, and that is multiplied by your x3. Okay, so this is your x1, x2, and x3. Okay, so from here now we can say that the solution space is spanned by u and v. So what is our u? Our u is this, and our v is this. So we have been able to produce two vectors from this particular equation, and then from there, remember the question says present two vectors that span the solution space of this system. So these are the two vectors. So the two vectors we are looking for are okay, I can write that here. Therefore the vectors are, we can call them u equal to 0.31 and 0, and then v equal to 0.20 and 1. And then we can imply that the system that, or the equation that was given there, let me still use system, is equal to the span of this u and then v, and then that concludes the solution that is required there. Okay, so those are the two vectors that span that particular equation. Spanning means that they produce all the solutions. All you need to do is to get the values for x and then, for x2 and x3. Just fix any value for x2 and x3, and that will generate a solution for that particular system. Any value you put for x3 and x2 will give you a solution. And then there is CII, which says that we should also explain this geometrically. Okay, so also explain what we did in I geometrically. Explain this span geometrically. So how do we do that? Geometrically. Okay, so to do that, we are going to just show that or explain that the solution set is a plane through the origin. Okay, is a plane through the origin. Okay, and you can confirm that, okay, by trying to check the same thing we did in the previous example. That's to form the equation of the plane. So you can discover one or two things. Maybe you will discover that the normal excuse me. Okay, so if you go up in there is one example we did up. Let's see. Okay, yeah, here. Okay, so one of the things we discovered is that because it passed through the origin, all of these were zeros. Okay, so you will discover that if you try to formulate the plane equation for this, that you may have something that looks like that. I will allow you to decipher that on your own. Okay, so but in my thinking and from what I am seeing from it, you will discover that that particular span will pass through the origin of the plane. Okay, so let's try to ascertain that. All right, and then we go to D. So what is D saying? It says we should find the basis and dimension for the null space, okay, of the matrix. All right, so what are we invariably asked to do? So first of all is to see the matrix they gave us. They gave us the matrix this. Where is it? Okay, the matrix there is we have, did they give it a name? No name. -3 is a 3 by 5 matrix. a 3 by 5 matrix, minus 3, let me use white here, then 6 minus 1, 1 minus 7, and then we have 1 minus 2, 2, 3 minus 1, okay. Okay, so this is what they asked us to find, the basis and dimension. Okay, so because they are saying the null space of it, so that means the other side of the equation, assuming it were to be an equation, will all be equal to 0. So that means let's transform it into that what do you call it, augmented matrix. So what it means is that we can actually add zeros to this if we want, or we can leave it this way, because with or without those zeros it will still be zeros on this place even if you don't put it or you put it, okay. So that means this, if we now try to do a reduction, of course we have to reduce to be able to know the ones that are linearly dependent, and that will bring out the basis for the matrix. Okay, so let's go. So remember, in our reduction, row 1 will remain the same, but here we will want to exchange row 1 and row 2. So I'm going to have 1, 2, minus 2, 2, 3, okay, 3 minus 1, and then if I'm correct, and then, okay, I think that's all, and then 0. Okay, so the second one now should be our maybe 3, okay, that's equation 1 now, okay. So here will be 6, 1, sorry, minus 1, 1, and then minus 7, and then we have 0 here, and the last one is 2 minus 4, and then we have 5, and then we have 8, and then we have minus 4, 0. Okay, for the sake of space, you can do the reduction somewhere, and I will tell you what to bring in here because of space in your material. All right, so let me try to reduce this a little, okay, so that I'll be able to reduce the rows here. Okay, so see what we are going to have here. So here we are going to have, this is going to remain as 1 minus 2, 2, 3, and minus 1. Okay, so 0 will be there. Now in reducing this, we are going to use R2 plus 3R1. The reason we needed to exchange, I know I've said it before, is that we want the pivot to be 1, okay. So if we are, so it will be easy for us to write all of this algorithm. That's actually why we usually do that. Okay, so see what's going to happen here. We will have 0 here, so this 3 times this will be minus 6. Yeah, let me be sure of what I have there. Remember, sorry, that this is 6 and not minus 6. Is the second, the third number that is minus 1. Let's not make mistakes here, please. Please, let's check this and be sure that is correct. Okay, 2 minus 4. And then 5, 8 minus 4. Okay, so let's go on now. So this plus 3 times this is also going to be 0. And then next, this plus 3 times this. Remember, this one now is 2. So this plus, okay, minus 1 plus 3 times this. 3 times that will be 6. So you have 5 here. And then do the same thing here. 1 plus 3 times this, which is 9, will be 10. Do the same thing here. Minus 7, 3 times this is minus 3. That will be minus 10. Okay, and then here, of course, will be 0. All right. So now here will be, so to reduce this one, but before we continue, you are aware that you can actually, remember I've said it before, you can cancel out if there is a common factor, and you can see 5 can cancel out all of that. 5 here is 1, 2, and minus 2. So we are going to have 1, 2, and minus 2. So let's write it 1, 2, and minus 2. So then let's go over here. This one, the algorithm will be R3 plus, since the signs are the same, we do minus 2 times R1. Remember, we are still using R1 as the pivot. So this is going to give us 0 here. And then in this case, 2 times, minus 2 times this is 4. Here will be 0. Minus 2 times this, that will be minus 4. Here will be 1. And then minus 2 times this, that will be minus 6. That will be 2. Minus 2 times this, that will be plus 2. That will be minus 2 here. And then here will be 0. And you will see something immediately. And what is that? You will immediately discover that our row 3 is the same as row 2. Okay, so if you now transform by saying row 3 minus row 2, so you want to now replace row 3. So this is going to be 3 minus 1, 0. So here will be 0, 0, 1, 2, minus 2, 0. And so everything here will be 0, 0. Remember, you are transforming with R3 minus R2. Okay, because actually your intention is to make here 0, but you will end up eliminating everything in your row 3. And so since row 3 has been eliminated, so it means that only our row 1 and 2 is left. So that means our x2 is missing. So x2, let me use white. So x2 is a free variable. There are only 2 leading variables here. That's x1 and x3. So x2 is missing. x4 is a leading a free variable. x5 is also free variable. So you can then use that to make some conclusions there. Or let me still leave it that way. Okay. So we can use that to make some conclusions. And what is that? So we can conclude that since x2, x4, and x5 are free variables, or you can just say, are free variables. So it implies then, let me remove this implication here. So it implies therefore that the dimension of that particular the set of vectors given to us, or the matrix given to us, the dimension is equal to 3. Okay, so that's giving us the number of free variables that we have left, and then we can get our basis. Okay, and then we can get our basis from there as well. Okay, so and how do you see that? You can easily see our basis from here. And what are you seeing? You can see that this guy here is a multiple of this guy. If you can see that. And so we can strike out one of it. And you can also see that this guy also is a multiple. Let me use red for that one. You can also see that this one is a multiple of this one. Okay? So you can also strike out one of it. So the basis, therefore, so our basis is going to be the set of the first one here. Okay. Okay. All right. Let's go this way. So let's first of all set the solution now. Okay. So if we set the solution, in fact, if we solve this finally, you are going to discover something from here now. You are going to fix, let me remove all these things I put there so that we can be seen. But from what I said now, you have already known that our, our the remaining linearly independent ones are just going to be 3, that 2 of them are going to go out. Okay, so and that will give you your basis to be 3 sets. But before we obtain those 3 sets, let's try to get the solutions from here. So from there, you will see that you are going to have that the whole of this. Let me try to write out the equation. So our equation 1 is going to be x1 minus 2x2 plus 2x3. See, I'm writing from here, multiplying with x, and then plus 3x4 minus x5 will be equal to 0. And then the equation 2 is going to be, it starts from x3, so you just have x3 plus 2x x4 minus 2x5 will be equal to 0. So we will have about 3 free variables, which are x2, x4, and x5. So what will happen now is that we will fix them to themselves. So we can say, okay, I think this board is finished. Am I correct? Let me see. Okay, I think that's all. Okay, so we can say let our x2 be equal to x2, and then our x4 equal to x4, and our x5 equal to x5. So that means we are going to write x3 and x1 in terms of those 3. So let's see. So what it means is that from equation 2, our x3 is simply equal to minus 2x4, then plus 2x5. Okay, and you can keep that there. So that's our x3. Okay, and then our x1 will be equal to, look at our x1 here, which is here. Okay, so take every other thing to the other side. So we have x2 will be here, so you are going to have positive 2x2 minus 2x3 minus 3x4, and what again? Then minus x5 will come over to also give us plus x5. Okay, so so you have plus x5. Okay, so if we now substitute x3, we are going to have 2x2. Let me use this. Our x3 is minus 2x4 plus 2x5. Then we bring in minus 3x4, then plus x5. So what will that give us? So we just have 2x2 here plus 4x4, then minus 4x5, then minus 3x4 plus x5. And if we collect like terms, we are going to have that x1 is equal to 2x2, then this minus this will give us x4 only, and this one plus this will give us minus 3x5. All right, so we have gotten all of the equation, all of the values. So I'm thinking if I can finish this here instead of going to a new page. So let's now try to write our solution. So see what our solution will be: x1, x2, x3, x4. That will help us to get the basis that we are looking for. It will be equal to okay, remember, okay, that's going to be equal to, here, what is our x1? Let me remove this so I can see it. Okay, it's not showing there. Let me bring it up then a little bit. Okay, so I think I can see it now. You can stay there, stay here. Okay, so we can remove this now. So our x1 is equal to, let me use this, 2x2 plus x4 minus 3x5. You see everything is in x2, x3, and sorry, x2, x4, and x5, because they are the free variables. and our x2 will be equal to x2 because it's a free variable. We fix that. X3, we got it here as minus 2x4 plus 2x5, and then our x4 will be x4 because it's fixed. Our x5 will be x5 because it's fixed. Permit me to put off this thing making noise. Okay, let's try to finish up this before. Of course, I can end here because this is the end of question 5. So from here we can, let me remove this place and have space to write this. So from here we can now split this into x2, x4 and x5, and that's going to give us x2, we have 2x2, then x2 here is 1, the x2 here is minus 2, and x2 here is 0, x2 here is 0. So this will multiply x2. Then we come to x4. x4 here is 1, x4 here is 0, x4 here is x2 in the third one is 0. There's no x2 there. Okay, so it's 0. Then x4 here is that minus 2, x4 here is 1, x4 here is 0. So this one will multiply x4. And then finally for x5, you are going to have that your x5 in row 1 is equal to, x5 in row 1 is equal to minus 3, in row 2 is 0, in row 3 is 2, in row 4 is 0, in row 5 is 1, and that's multiplying your x5. Okay, so that has given us the full solution set for your x1 to x5 in that system. So that means this vector, let's call it v1, v2 and v3. So these are the basis for that particular matrix, and all of them depend on x2, x4 and x5. Okay, so these are the basis, and then there are 3 of them, and that's why we have the dimension to be equal.